Here in problem 1, we're told that in 2012 the population of a city was 5.75 million and that the exponential growth rate at that time was 1.89% per year, and we are asked to answer these questions. So the first question is this. Here's the first question. A, find the exponential growth function. Okay, now that's the function. So the exponential growth function, I'm going to write it like this. I'm going to write P of t, meaning this. This is the population, and it says depends on time. Right, so the population of the city depends on time. That's what this tells us here. Population depends on time, and time is in years. And the model for population exponential growth is P naught. Now that's the initial population. So this is the initial population, and that's the population in 2012 because that's when things start. And then it's E to the KT. Now this K, that is the growth rate, and T is the time in years since 2012. All right, so here's our function. Let's make it a little clearer. P of t is equal to P naught E to the KT, and for us, we're going to have P of t is equal to, now the population in 2012. Well, the population in 2012, this P naught right here, that's the initial population. That's our start value, and that is the 5.75 million. So I'm going to put that 5.75 million right there. 5.75 e to the k. Now, what is this k? Well, that's the growth rate, and our growth rate is 1.89% per year. So I'm going to write that number here, but I'll write as a decimal, 0.0189t. And this is part A. That's the answer to part A. That is our exponential growth function. Now in part B, here's part B. What we want to do is estimate the population of the city in 2018. So how about this? In 2018, what is T? Well, let's subtract 2012. That means T is equal to 6. So we're 6 years from the start, 2012. So let's put 6 in for T. So I'll put that 6 right in here. So here's how I'll write it. P of 6 is the population 6 years after we start is 5.75 e to the 0.0189 times 6. Well, this is a calculator problem. So on my TI-84, I'm going to type in 5.75. Then I'm going to press the second key, and then the LN key. Now, these are both on the very left side of your keyboard, because right above the LN key is the key e to the x. And that's what we want here, right? I want that e to the x because that's what I'm going to put in here. E to the, here's x. All right, so put in second, press second, the LN key, you'll get e to the x. Now, when you do that, when you actually do that, what you get is e, and then your cursor comes up here. So up there, you're going to type in 0.0189, and then press the times key and press 6. Okay, that'll give you the exponent. And then press enter. Now when I press enter, I got this. I got P of 6 being 6.4404 ... It keeps on going. But here's what I'm going to do. When I look up to the original problem, it was given to, the population was given to 2 decimals. So I'm just going to write this as 2 decimals. So it looks like the third is a 0. So I'm just going to round this to 6.44. So estimate the population in 2018. I'll say in 2018, the population was approximately 6.44 million. in part C, we are trying to find when the population will be city. Now that will be 9 million. So when? Now that means find t, right? When, that's the time. So what I want to do is I want to use this formula, and I want to find when I want to find t when the population is 9 million. So here's what we have. We're going to have that I want this to be 9 million. That's equal to 5.75 e to the 0.0189 t, and we are trying to find this. Okay, find this. How about if the first thing we do is this? I'm trying to solve for t, so let's divide by 5.75. So here's what I'll have. 9 divided by 5.75, that's equal to e to the 0.0189 t. And now I want t, and I see t is in the exponent, so I'm going to undo that exponential using a log function. Now since the base is e, I'm going to take the natural log of both sides and write this. The natural log of 9 divided by 5.75 is equal to the natural log of e to the 0.0189 t. And this I can simplify over here. So here's what I'm going to have. The natural log of 9 over 5.75 is equal to, now, the natural log of e, the bases match. This is log base e of e to this power. So I'm just going to get the exponent, 0.0189 t. I mean, that's why we take the natural log, so I can undo, the natural log undoes the exponential. So now all I have to do is divide by this 0.0189. So here's what I'll have. We'll do it at the top right here. T is equal to, all right, it's going to be this fraction. I'm going to divide by that 0.0189, and I'm dividing this. The natural log of 9 over 5.75. So in my calculator, I'm going to press the log key. I'm going to press ln. I get parentheses, and then I'll type in 9 divided by 5.75. I'll close, and then I want to divide that by, press the division key, 0.0189. Now when I do that, I got t equals, I'm going to just write it as 23.7. I got 0.5. But how about this? Let's say in about 23.7 years from 2012. Now, if you add 23.7 to 2012, you get it. You get this. So I'll say that is in about 2035, the population will be 9 million. All right, so we start in 2012. 23.7 years from then, the population will be up to 9 million. Now, 23.7 years from 2012 is sometime in 2035. And in part D, we want to find the doubling time. That means how long does it take from any point in time, how long does it take the population to double in size? Well, let's think of it this way. In 2012, or we have a time now, say in 2012, the population is 5.75. Now we want to know when, right? Find the doubling time. When is this population here going to be double? So how about this? We want 2 times, I'm going to write it like this, 2 times 5.75 to be equal to 5.75 e to the 0.0189. Let's see if that makes sense. Here's the current population. We want to find, I need a t here. Here's the current population. We want to find when, find t, so when this population is doubled. So it'll be doubled, just multiply it by 2. Now an interesting thing here is when I try to solve this, what I'm going to do first is I'm going to divide, right? I'm going to divide by this 5.75. Let me write that so it's actually readable. I'm going to divide by the 5.75, so it'll look like this. 2 times 5.75 divided by 5.75 is equal to 5.75 e to the 0.0189 t divided by 5.75. This cancels, and I get this. I'll do it at the top right. 2 is equal to e to the 0.0189 t. So the initial population, you see that it just dropped out. It canceled out. So it doesn't matter what initial population you start with. We're starting with 5.75, but it doesn't matter. Put any number here for the initial population, and it will cancel out. So no matter what the initial population is, we're going to end up with this equation here. Now solve this for t. So t's in the exponent, so it's an exponential. So solve exponentials by taking logs. The base is e, so I'm going to use the natural log. So we will have natural log of 2 is equal to the natural log of e to the 0.0189 t. Gives me the natural log of 2 is equal to 0.0189 t. If I divide, so I'll get t is equal to the natural log of 2 divided by 0.0189. So let's do that on our calculator. I'm going to press the ln key. I get a parentheses and a 2. Divide by 0.0189. And I got t equal to 36 point, maybe 6-7 years. All right, so the doubling time for our situation here is 36.67 years. Okay, now before we move on, let's look at this doubling time idea. The doubling time, right, here's what we got in our problem. We got this. T is equal to ln2 over 0.0189. But what is this 0.0189? If you come back to the model, all right, the model is actually this. P of t is equal to P naught, the original population, e to the kt. And you see what that k is? That is this number right here. So in general, the doubling time, all right, here's a little formula for the doubling time. And we could solve it like this every time, but the doubling time is going to go like this. T is equal to ln2 over k. There's a formula for the doubling time.